Question 3. A student determined the enthalpy of combustion of cyclohexane. So let's have a look what we've got in the question. We've got 50 grams of water being heated by cyclohexane being combusted or burnt. We've got the initial temperature of the water. We've got the amount of fuel being burnt if we subtract those two numbers. We've got an enthalpy change for burning 1 mole, so in kilojoules per mole, so the kilojoules of energy that are released from burning 1 mole of cyclohexane. We've got specific heat capacity, and we've got the relative formula mass of the cyclohexane, 84.0. So we're looking immediately at using delta H equals minus mc delta T, or Q equals mc delta T. I always put the minus in and use delta H equals minus mc delta T because that gives you the enthalpy change, the heat energy released, which should then match the minus value on the enthalpy of combustion, because combustion is an exothermic reaction. Now we know that delta H is minus 1216 kilojoules per mole. So what that means is that when you burn 1 mole of the fuel, that's the amount of heat energy that you get released per mole. So I'm getting 1216 kilojoules of energy if I burnt 1 mole of the fuel. So the actual mass of the fuel burnt, if I subtract the two numbers from here, so the initial mass and the final mass, I can work out that I've got 0.63 grams of the fuel burnt. So the MR of the fuel is 84, so moles is mass divided by MR. 0.63 is the mass burnt divided by 84. I've used up 0.0075 moles of the fuel. So now I've got the amount of number of moles of fuel that I've burnt. If 1 mole of a fuel releases 1216 kilojoules of energy, then 0.0075 moles releases 1216 multiplied by 0.0075. It releases minus 9.12 kilojoules of energy. Now, the kilojoules needs converting into joules for this equation here, so delta H here is in joules. So I'm going to multiply by 1,000, so it's 9,120 joules. So that's the amount of energy in joules that will be released or should be released by the amount of fuel that I've got burnt. So I can put this into my equation now. So this is the heat energy that should be released in my experiment. 50, remember, 50 is the mass of the water being heated up, so M is 50 grams. So this M here is the mass of the water being heated up, nothing to do with the fuel at all. 4.18 is the heat capacity, specific heat capacity of the water, you'll always be given that, and delta T is what we've got to try and work out, so that's the heat change for this reaction. If I multiply these two together and then 9,120 divided by 50 multiplied by 4.18 comes out as 43.6. I've got a minus on this side and I've got a minus on this side, so I've got a minus divided by a minus, so it's a plus value. That's correct because the heat change, the temperature change will be a positive value because the temperature is going to go up as I burn a fuel underneath the beaker. So that's correct. Now what it wants to know is what the final temperature is. So I've got the temperature change here. The initial temperature was 19.1. It's gone up by 43.6. That's been the change. So if I add these two together, it's gone up to 62.7. I've decided to use it to 3 significant figures because in my question here I've got something to 6 significant figures, but I'm always looking to find the lowest number of significant figures. 84.0 is 3, 4.18 is 3, 50.0 is 3, 1216 is 4. The masses here are to 6, the initial temperature is to 3, so I always take the lowest number of significant figures in my question, which is 3, and that's why I'm putting this to 3 significant figures. A data book value for the enthalpy of combustion is minus 3920. The student concluded the temperature rise recorded in the experiment was smaller than it should have been, to suggest a practical reason for this. So the enthalpy change should be higher than it is. The reason is that you've got heat loss to the surroundings. Other reasons are that the fuel didn't fully combust, incomplete combustion, and the vessel might actually heat up, so the beaker might heat up as well, absorb some of the heat instead of that being registered on the thermometer. Table 2 gives some values of standard enthalpies of combustion here. So I've got standard enthalpies of combustion. Use the data to calculate the enthalpy change for the reaction represented by this equation. So I need to use Hess's law here. So I've got to work out the enthalpy change for this reaction. Now the enthalpy change is independent of the route taken. So I've got some other equations here. I've got some other enthalpies of combustion, and I can come round this way, and by adding all of these together, I can work out this enthalpy change. So carbon going to carbon dioxide, so enthalpy of combustion will be carbon being burnt in oxygen to make carbon dioxide is minus 394, but that's for one carbon, and I've got 6 here. So to turn carbon into carbon dioxide, enthalpy of combustion, it's 6 multiplied by 394, which is minus 2364. Remember, the minus has got to stay in place because it's releasing energy. I've got the enthalpy of combustion of hydrogen. Hydrogen and oxygen are going to make water. But again, I've got 6 H2O and I've got 1 H2O here, so it's minus 286 multiplied by 6, which is minus 1719. And I've got the enthalpy of combustion of the cyclohexane, C6H12, going to form the carbon dioxide and water. I've got this one here. Now I've only got one of these, and I've got one of these here, so minus 3920 is correct in this direction. Now then, I've got this equation, and it's come from here to here, here to here, and it's got to go from here back to here to match that one. So if I'm going in this direction here, all these arrows have got to come in this direction, so I've got to reverse that sign. So this one, this one is minus 2364. I've done that, it's in the right direction. Minus 1716, it's going in the right direction here, but this one needs reversing. It doesn't need multiplying by anything, because I've got one cyclohexane, I've got one cyclohexane here, but it does need reversing, so that should be a plus 3920 to come round in this direction. So I've got minus 2364 minus 1716 plus 3920. I've got equals, and this will be in joules. So and then I divide by 1,000 to get it into kilojoules, because it asks for it in kilojoules, or actually it doesn't ask for it in kilojoules, so you could leave it as 160,000. I could leave it as let's just have a quick look. Oh, sorry, all of these in kilojoules anyway. Sorry, all of these are in kilojoules anyway. So minus 2364 minus 1716 add 3920 comes out as 160 anyway. So I don't need to do any conversion. It's not specified what kind of units it's going to be in. And if you look in the equation in the table here, it says kilojoules per mole. So it just comes out as minus 160 kilojoules per mole. So that's fine. We'll just leave it as it is.